All right, AEW number 9. So find out where the function is concave up. And that means that the second derivative is positive. And then I already graphed it. Let me double check. Y is equal to 2 cosine x plus cosine of 2x, and it's in radians. And so this is the graph. So let's see, where does it look concave up and concave down? So this part in here, that looks concave down, and then somewhere approximately in here, which is a little bit less than a 1.0, then this part, maybe I should use a different color. This part looks like it's concave up. And then this part is concave down. And then this part looks like it's concave up till maybe right about there. And this part looks like it's concave down. And then 2 pi would be approximately right here. So it said, pretty sure I put, yeah, from 0 to 2 pi. So it looks like we're going to be looking for 1, 2, 3, 4 places where the second derivative equals 0. And then we could find out the intervals where the second derivative is positive or it's concave up. So we're going to be looking for 4 answers for the second derivative. Okay, so for the first derivative, the derivative of 2 cosine, that's going to be negative 2 sine of x. And then for this one, the derivative of cosine of 2x is negative sine of 2x. And then by the chain rule, you need to take the derivative of 2x, so that's a 2. And I'll just put the 2 in front. Now for the second derivative. So the derivative of sine is cosine, so this one will be negative 2 cosine of x. And then very similar right here, it's going to be negative 2 times cosine of 2x. And then you need to do the chain rule again. So multiply by another 2. And then set it equal to 0. On the right side, there's a negative 2 right here and a negative 2 right there. So I could factor that out. And then it would leave cosine of x. And then since I factored this negative 2 out, it's going to leave behind positive 2 cosine of 2x. So of course, negative 2 never equals 0, but this could equal 0. So when does cosine of x plus 2 cosine of 2x equals 0? And by looking at the graph, we're looking for 4 solutions. So in solving trig equations, there's 2 main ideas that you should try for. One is get the same trig function. That we already have, cosine and cosine. The other important thing is that the arguments are the same. So either get them both to have 2x or get them both to have just x. And what I could do is, for the cosine of 2x, there's an identity. So use a trig identity. And so for cosine of 2x, there's actually 3 identities. The one that I remember is it's cosine squared minus sine squared. But if I use that identity, then I'm going to be introducing sine squared into the problem, and I want it to be all cosines. So for another identity, you could just leave the cosine squared there, and then replace sine squared with 1 minus cosine squared. Then if you distribute the negative, this is actually going to become a positive cosine squared. Together with this first cosine squared means there's 2 positive cosine squares. And then minus a 1. So that's the identity that I'm going to use in these parentheses over here. 2 cosine squared x minus 1. And then if you distribute the 2, it's going to have 4 cosine squared. And next I would put this term, the single cosine, so plus a single cosine. And then distributing this 2 over here means there's going to be minus 2, and then that's equal to 0. Daisy, do you have any questions yet?
No, not yet.
Do you know what I'm going to do next?
You have to solve for the x's, right? You want to combine the cosecants?
So you can't combine them because one of them is squared and the other one is not. So if this was pre-calculus, right now we would be looking at this. So that's what it would look like in pre-calculus. And you know what formula I would need to use to solve this?
Wouldn't it be the quadratic?
That's true. So I would do the quadratic and I would go x equals, and I would do the quadratic formula. But this one isn't just x, this one is cosine of x. So instead it's going to say cosine of x equals the quadratic formula. So the b is a 1 that is sitting in front of cosine. So negative b plus or minus the square root b squared minus 4 times a, which is a 4, and c, which is a negative 2. And then all divided by 2 times a. So let me simplify this a little bit and I'll put it in the calculator. So 1 squared would be 1, and then a negative times a negative will be positive, and then this is going to be 16 times 2 is 32. So inside the square root, there's a 33. And then it's divided by 2 times 4, or 8. So for that, I need a calculator. So negative 1 plus the square root of 33. And then that whole thing gets divided by 8. 0.593. And then also do the quadratic formula with minus in front of the radical. So a 0.593 and a negative 843. So that means that cosine of x could equal a 0.593, or cosine of x could equal a negative 0.843. So the cosine function looks like this from 0 to 2 pi. And then we're trying to find out when does it equal a 0.593. And if you make a horizontal line going straight across, there's actually going to be 2 times when cosine will equal a 0.593. And one of them comes from just asking the calculator, what's cosine inverse of a 0.593? So make sure it's in radians. Yes, it's in radians. So then cosine inverse of a 0.593 is a 0.936. So sort of running out of space. X equals a 0.936. Is that what it said? 936? 936, yes. So that means that on the x-axis, if you go from here to where that green dot is, that's a length of 0.936. And because the graph is symmetric, you could also go from the 2 pi and go to the left to find out where the second green dot is. So that means that the second answer is going to be 2 pi minus 0.936. So 2 pi minus the 0.936. So another answer is 5.347. So let me just collect my answers over here. So x equals 0.936 was 1, and then the second one I got was 5.347. So I'm looking for 4 solutions, and the other 2 solutions come from this part, which says if you look at the cosine graph from 0 to 2 pi, and down here is a negative 0.843, and then goes straight across from there, and there's going to be 2 solutions. And then one of them is going to be cosine inverse of the negative 0.843. So skip over to the calculator. Cosine inverse of a negative 0.843. So a 2.574. So next, the third answer is 2.574. So that's this green dot, which is now a black dot. And then you could do the same thing to find this fourth answer, go 2 pi minus what I just got. So 2 pi minus a 2.574. 2 pi minus the 2.574. 3.709. And that's the fourth one. So 2, don't do that. Not 3.709. And let me see, this is actually the smallest one, and this is the next one. So then I'm going to go look at the graph and see if these make sense. So go back to the graph. And I was thinking that I was estimating that right about there, it changes from being concave down to concave up. So my estimate wasn't too bad, but actually it should be this point. The first one was 0.936. So that's one point where it changes. And then this part is concave up until approximately right here. Now let's see how good my estimate is, because the second answer I got was a 2.574. Off by a little bit. So between those first two, that's concave up. And then from the third answer, which would be approximately right here, to the fourth answer, approximately right here, that would also be concave up. So for concave up, so that would be between these two. So from 0.936 to 2.574. And then also from this one to that one. So 3.709 to 5.347. That is where it's concave up. Well, Daisy, do you have any questions?
No, not right now. Like it just seems easier like now practicing more problems because I just got done with the homework assignment yesterday and it was like questions like this, but it just took me a while because it's more new.
Right. Yeah. And you got to be careful because if you make one little mistake, like at the beginning, you forget that chain rule the second time or something like that, then everything else after that's going to be wrong.
Yeah.
When I the first many years when I was teaching calculus, I would say problem number one, find out the minimum, the maximum, where it's increasing, where it's decreasing, where it's concave up, where it's concave down. And if a person made one little mistake like this at the beginning, let's say they forgot that too, everything after that is wrong. So then I decided to start asking the questions like this, just do one thing. Where is it concave up? That way, if they do make a little mistake, then it would only be, minus 1 point because of that little mistake. Anyway, on to number 2. Every time I make these up, I put more and more space thinking, oh, this is going to be plenty of space.
And it's not.
And when I sort of do my work on paper it is.
Yeah, it's like enough space. Like I have the extra.
Yeah, with the iPad, it seems to take up more space. Okay, for number 2, so this is an optimization problem because we're supposed to find the least amount of material. So in other words, create a function and then find the minimum. So it's a cylindrical soda can. So it looks about like this. And then the base is a circle, so I'll have to use R for radius. And then this will be the height of it. And with these word problems, there's a part where you do algebra, and then there's a part where you do calculus. First of all, if it's going to be 12 ounces, well, that's equivalent in cubic inches to 2.166. And then cubic inches means a volume. So the volume for a right circular cylinder. Daisy, do you know what the formula is for the volume?
Isn't it 1/3 pi r squared?
So that sounds more like if it was a sphere,
Okay.
like a basketball. So it doesn't have 1/3. So it has pi r squared. Just the pi r squared itself, that would be the bottom of it, because that's the area of a circle. And then you have to have circles like that stacked up, h tall. So then it's going to be times h. And I could then substitute in this number, 2.166 equals pi r squared times h. And with this equation, this is not the equation that we're going to be taking the derivative of. So I'm just going to leave this because I don't know exactly what I'm supposed to do with it. I know that I'm probably going to have to either solve for h or solve for r. But at this point, I'm not sure. So I'm just going to wait on this. So next for the calculus part. So this is what we're supposed to find the minimum of, the amount of material. And the amount of material, well, it's got to have a top and a bottom. So the top and the bottom are both circles. So that means that the area is pi r squared. So the surface of the can is made of two circles whose area each are pi r squared. And then for the side of the can, well, the side of the can is actually made out of a rectangle. And you just take a rectangular piece of metal, and then you can go like this, and then you can make it into a circle. And so that is the side of the soda can. So if you cut down the side, you could flatten out the piece of metal, and then it would be a rectangle. Well, this right here, that's the height h that I already have on the picture. And then for this top part up here, well, once it becomes a circle, then this top part right here, that's the circumference of the circle. So the formula for circumference is 2 pi times the radius. So that would be the top if you cut this and then measured this, or opened it up and made it a flat rectangle, and then multiply by the height. Okay, so this is the function that I need to take the derivative of. And I've got too many variables. On the right side, there's both r and there's h. And that's the reason that I needed this equation. So what I think I'm going to do is solve for h. Because if I solve for r, it's going to have a square root, and then that's going to make taking the derivative more complicated. So I'm just going to solve for h. So leave h on the right side, and then divide both sides by pi r squared. And then that is going to get substituted in for this h right here. So surface area is equal to 2 pi r squared plus a 2 pi r, and then replace h with a 2.166 divided by pi r squared. And then it could be simplified a little bit. So 2 pi r squared, that doesn't need to be simplified. I could have this pi cancel this pi, and I could have this r cancel one of these r's. And then I just need to know what's 2 times 1.66. 2 times 2.166 is 4.332. So for the numerator, there's a 4, which I was using a black pen, 4.332, and in the denominator, there's just an r. So sometimes what I like to do is take a break before I take the derivative and actually graph this function and see, does it actually have a minimum? Because if it doesn't, if the graph looks like this and it only has a maximum, that means that I did it wrong. So I want to graph it. So 2 pi r squared plus 4.332 r. Except with this calculator, I can't use r. It's going to be 2 pi x squared and then plus a 4.332 divided by x. And so we don't need the negative part because the can can't have a negative radius. And it does have a minimum. And it's actually when the radius equals a 0.701. Because I was using X instead of R. So I should get the answer 0.701. Now let's see, do I get 0.701 for R? So then take the derivative. So S prime equals, and the derivative of this R squared is going to be just 2R. So that means you multiply with the 2 pi, there's going to be 4 pi R. And then that one's done because we're taking the derivative of S with respect to R. So there's no extra R prime or anything right here. Also, I know that there is not an R prime because R prime means how fast is the radius changing, as if this soda can could grow or shrink. That's when the radius would change. So it doesn't have an R prime. And then the way that I look at this one is, I know that the derivative of 1 over x is negative 1 over x squared. So that's one of the derivatives that shows up a lot, so I just remember that one. So that means this one is going to be negative 1 over r squared, and the constant 4.332 just stays there. Then set the derivative equal to 0, and supposedly we're going to get a 0.701 is the answer. So if you set this equal to 0, you could then take this negative term and move it over to the left side or add it to both sides. So it's now positive 4.332 over r squared on the right and 4 pi r on the left. Now I only have about 2 or 3 more steps of algebra. One would be collect all the r's together, so multiply both sides by r squared. And put all the numbers on the left side, so divide by 4 pi. So on the left side are just the numbers. 4.332 gets divided by 4 pi. And on the right, that's going to be a total of r cubed. And then finally, to solve for r, take the cube root of both sides. So we need the cube root of 4.332 divided by 4 pi. And supposedly, I'm going to get a 0.701. Hopefully. All right, so I need the cube root of 4.332 gets divided by 4 pi. And I think I'm going to get the answer wrong. Daisy, you know why I got the answer wrong? The hint is I didn't type it in right on the calculator.
Oh, is it because of 4 pi's in the cube root?
Well, it's supposed to be in the cube root, but the calculator, because I didn't put the 4 pi in parentheses, the calculator thinks you're only dividing by 4. So right here, I should have put parentheses, 4 pi, not a 9. There we go. And then that should be the 0.701. Yay, it worked, 0.701. And then the last thing is, it said find the dimensions, and I found the r, but I also need to find the h. So then I could just use this right here and plug in what I got for r, and then h will be a 2.166 divided by pi, and 0.701 is squared. 2.166, 2.166, and then divided by, and then there was a pi, and the 0.701 gets squared, and then parentheses around the whole denominator, and the height is 1.403. And that was in inches. So something about this problem is not very realistic, because that means a soda can would be like 1.5 inches tall. So you'd be drinking a soda can like this. It'd be better to be drinking that small amount of soda. Perhaps when I looked up 12 ounces, maybe I Googled it and it put 1 ounce. Well, anyway. Hey, Daisy, do you have any questions on that one?
No, not right now.
Okay. Next up, just practice doing some graphing, which is basically a good way to understand what the derivatives tell you about the function, but without actually having the function. So for the first one, f of 0 equals 1, so there's a point on the graph. So that part is done. And the derivative equals 0. So that means that it would be a horizontal tangent line. So I'll just put a little horizontal line right there to remind me. That one's done. At x equals 1, the derivative is equal to -1. So this one is saying that the slope, so wherever you are, I don't know where the point is, whether it's here or here. I'll just pretend that it's right here. But this should be a slope of -1, which looks approximately like that. And then on the other side, when x equals a -1, then it's going to have a slope of +1. So something approximately like that. All right, those are done. Then at x equals 0, the second derivative equals a -1. Now the -1 isn't important. All that's really important is that it's negative. And then negative means that it's concave down. So I'll just put something like this to remind me it's supposed to be concave down there. And then at x equals 1, the second derivative is equal to 0, so it's supposed to be changing concavity. So that means if this side is concave down, then this side should be concave up. And at 1 is where it changes. And then also at -1, it's going to change concavity. So this should be concave up. Okay, now I need to redraw it and see what my graph really should look like. So I think that, and basically, if I just move this part down and then go like this, I think that's basically going to do it. And then I could just erase this part. Yep. I'm not quite satisfied. That's because at this point right here, that's where it's supposed to be changing concavity. But by looking at my picture, it's more like right there is the inflection point. Okay, so this part could be concave down until I get to the -1 and the +1. And then I could have it change concavity I think that's better. And then take my little magic lasso. All right, there's part A. Let's see for part B. So it also starts with a point at 0, 1. At -2, the derivative does not exist. So let's say over here is -2. And then I'm just going to make like a little cusp because that's where the derivative does not exist. The derivative at 0 is equal to 0. So that, like the last one, is a little horizontal tangent line right there. Oh, and this is a typo right here. That was supposed to just be a 1. So this part, because I was saying right here, I was saying on the left side of the graph, so all of this, it's supposed to be concave up. And then right there, I had a -1, but that's supposed to be a +1. Okay, so on the left side, it's supposed to be concave up. Well, if you look at this little cusp that I just made, on each side, that's concave down. So if I just switched it like this, then each side would be concave up. So the cusp idea was good, but I think I should have it going in this direction because that's concave up. And then this is all concave up. And then it could flatten out right here. And at 1, the derivative is supposed to be equal to 0. So actually, because there's no other rules that I have to follow, what I could do is just go like this and make a horizontal line. Because then when you get to 1, the derivative would, oh no, that's second derivative. Never mind, I can't use a straight line. I'm trying to make it easier. Okay, this is second derivative, so that means second derivative equals 0. That's going to be an inflection point. So that means that I just have to have it change concavity. So I could have it after it goes through where x is equal to 0, then I could have this curve down so that that part's concave down, and then this curve up, so that's concave up. And then that takes care of the second derivative equals 0 when x equals 1. And then I just erase that part. And then it's done. Daisy, have you done L'Hopital's rule?
I don't think so, not yet.
Okay. Well, I think you've seen it before because you've come to all of the AEWs, haven't you?
Yeah, I've heard you mention it before.
Okay. So L'Hopital's rule is for finding limits. So on part A, if you were to take the infinity and plug it in, the natural log of infinity is infinity. Just that part is saying, if you look at the natural log function, which looks like this, and you have x go out to infinity, so x is going to go that way, then the function is going up to positive infinity. So that's what the top part is saying. Then on the bottom, well, if x is going to infinity, that means the bottom is going to infinity as well. So L'Hopital figured out, well, there's an easier way to find out the limit. Since they're both going to infinity, then what you could do is just take the derivative of each one. That basically finds out, yes, they're going to infinity, but who is going there faster? Is natural log going to infinity faster, or is x going to infinity faster? So it's not the quotient rule, you just look at them separately. So for the purple one, the derivative of natural log of x is 1 over x. And then on the bottom, the derivative of x is just a 1. So it turns out that this is just going to be the limit as x goes to infinity for 1 over x, which means that it's 1 divided by infinity. And 1 divided by infinity is equal to 0. So the answer should be 0. Then what I'll do is I'll graph this function and then follow it out to the right, and it should be getting closer and closer to 0. So check my work with graphing the natural log of x divided by x. And if you follow this function out to the right, you'll see that it's getting smaller and smaller and smaller. The y value right there is 0.086. As you go out farther, the y value is dropping down smaller and smaller, so it looks like it's going to 0. So that one looks right. Then once students learn L'Hopital's rule, they're like, oh, that was easy. I'm going to do that all the time. So the derivative of sine of x squared. So it doesn't have parentheses, but it really means sine of x squared. So the derivative of sine is cosine. And then do the chain rule. So the derivative of x squared, that's going to be a 2x. And on the bottom, the derivative of x squared, that's a 2x. And then if you get a red pen, you can cancel out the 2x's. So what is the limit as x goes to infinity of cosine of x squared? Well, the cosine graph goes up and down, up and down, up and down forever. So that means that the limit does not exist because it has to settle down to just one number. So if it had done this, then I would say the answer is 0. But this one is always ranging from a top of +1 to a bottom of -1, and then back up to 1, back down to -1, back up to 1, etc. So that means it looks like the limit does not exist. And then to see if I did that right, then graph the original function and see what's happening as you follow it out to the right. So y equals sine of x squared in parentheses divided by x squared. That's not a squared. Squared. There we go. And then look at the graph and follow it out to the right. It doesn't even look like it's going up and down. Looks like the answer is supposed to be 0. All in here, it's a 0.
Yeah.
So that means that I did something wrong. And the thing that I did wrong is L'Hopital's rule could only be used. So you have the limit as x goes to whatever, just call it a. And then you have one function divided by another function. And then it has to be that it's infinity over infinity, like the first one was, or it has to be 0 divided by 0 at the beginning. And if it's not one of those two, you can't even be using L'Hopital's rule. Well, at the beginning, on the top, it's the sine function. And the very biggest the sine function gets is a 1. So that means that it's not going to infinity, and it's not equal to 0. So that means that I cannot be using L'Hopital's rule on part B. So I need to find another way to do it. And what I'm going to do is make an estimate of it. So like I was just saying, if this is the sine function, the very biggest it ever gets is 1. So that means that the whole function is going to be less than or equal to if you just put a 1 on the top. And then the bottom, I could just leave it like that. And then if you substitute infinity in, infinity squared or infinity times infinity is still equal to infinity. And 1 divided by infinity is equal to 0. So that means that the limit as x approaches infinity of the original problem has to be less than or equal to 0. And if it's less than or equal to 0, it doesn't really have much room to go, so it's equal to 0, which is what I was seeing on the graph. The y values are 0. Now, they're not actually 0, but they're so very, very, very close to 0 that the graphing calculator just calls it 0. So the answer is 0, but you can't use L'Hopital's rule to prove it. Oh my gosh, it's already 11:50. Let's see. We got those 2 word problems. Let's see if we could do both of the word problems. So a rectangular pig pen. Since it's a rectangle, I'm just going to call the sides X and Y. And the material cost $3 per foot for 3 of the sides. So I guess, since I like to save money, I would put the cheaper stuff on these longer sides. And then I could also use the cheaper stuff on this side. So now I have 3 sides that are $5 a foot. And then for some reason, you have to use, maybe that's where the gate is going to be. So it has to be more expensive. It's going to cost $8 a foot. So let's see, if the left side is X, that means the right side is X. But this is going to cost $8 a foot to make that. So the area, so that the pig has enough space, has to be 120 square feet. Well, area is just X times Y. So that has to be 120 square feet. And this again is the algebra part. And when I did this before with the soda can, I waited, but with this equation right now, if you solve for X or you solve for Y, they're both going to basically say 120 divided by something. So I think I'll just solve for Y. So just divide both sides by X, and then that's what Y equals. Then for the calculus part, find the minimum of the cost. So over here is going to be the calculus part. Whoops. So I'll use C for cost. Well, for the cost, there is 5x plus 8x. So that's going to be 13x for the left side and the right side. And then this is going to be 5y plus another 5y. So that means there's 10y for the cost. And then I have one of those situations where there's too many variables, x and y. So then just replace the y with 120 over x. So cost will equal 13x. That one could stay there. And then 10, and then replace y with 120 over x. And then take the derivative of that function. So the derivative of 13x is just going to be 13. And then 10 times 120, that will be 120 with an extra 0. And then the derivative of the 1 over x would be negative 1 over x squared. So negative over x squared. And then set the derivative equal to 0. And then take this negative fraction and move it to the left side. So it becomes a positive 1200 divided by x squared equals 13. And then we just have a couple steps of algebra. So you could multiply both sides by x squared and divide by 13. Or another way to look at it is the x squared and the 13 could trade places. So the x squared and the 13 trade places. And then finally, I just need to take the square root of 1200 divided by 13. The square root of 1200 divided by 13 is a 9.608. So x, is there more space over here? Yeah. X is equal to 9.608 feet. 9.5 feet? Could a pig live in that? Yeah, definitely. And then finally, use this equation to find out what y equals. So that's going to be 120 divided by x. So y is equal to 120 divided by that 9.608. Divided by that 9.608. And it should be about 12.5 feet or 12.49 feet for the y value. 12.49 feet. And Daisy, do you have any questions on that one?
No.
Now, I think the funny part is you go out to the farm and you tell the construction worker, I want you to make this by 9.60 feet by 12.49 feet. And they'll be like, you mean 13 by 10? Yeah, okay, good enough.
Yeah.
And let's do this last word problem. Made this one up myself. So there's this idea in economics, and that is the idea of diminishing returns. So if you owned a restaurant, In-N-Out Burger, and you only had one employee working, and they're not going to be very efficient. They would not be able to serve a lot of customers. So you go, oh, well, I have 2 employees. Yeah, that helps a little bit more, but you need more employees. So you keep going until you get like 40 people working at the In-N-Out. which actually, when the one in Seaside opened the first week, my son and I went and we counted, there was 42 employees. Anyway, so you just think, well, keep adding employees. They're going to be even more productive, but eventually they're going to be running into each other. They're not going to be able to be productive. So there must be some magical number of employees you should have. Well, instead of In-N-Out Burger, this is just a company that makes computers. And I'm going to say, here's the employees. And then here's how many computers they make. So when there's 100 employees, they can assemble 60 computers per day per employee. Then if you add an additional employee, so that would be 101 employees, then production actually decreases by 3 computers. So that means it would be 57. So the total production would just be, in this case, it would just be 100 times 60. So that would be the number 60 with 2 extra zeros. So the company would be putting out 6,000 computers per day. If it was 101 employees times 57, 101 times 57, then that equals 5,757 employees, which is actually worse. So maybe they should have 60 employees, or excuse me, maybe they should have 100 employees, or maybe even less. Maybe they could get by with 95 employees and they would still make more than 6,000 computers. Okay, so that's the setup. Now, how do we actually do the calculus? So I'm going to call employees X and computers Y. And because it goes up, or excuse me, because it goes down by the same amount each time, that means that it's talking about a line. And for a line, I don't need this anymore. You could find the slope. So subtract the 2 Y values. So Y2, 57 minus Y1, and then X2 minus X1. So that's going to be a -3 divided by a 1, or a -3, which is good because that's exactly what this is saying. It goes down by 3. So the slope is -3. And then find the equation of the line. I'm going to use this point right here. You could use either one and go y minus the y value of 60 equals the slope times x minus the x value of 100. And this is going to be -3x, and then distribute the negative times negative is a +300. And then add 60 to both sides. So y is equal to -3x. And then if you add 60, it's going to be plus 360. Now for the function that we're actually going to be taking the derivative of. So earlier I had done the total by multiplying the 60 computers per employee times the 100, and then that was 6,000 computers total. Well, in general, that means that I'm just multiplying the x and the y. So in general, the number of computers, I'll use C for computers, equals x times y. And then we could substitute this in for y. So the number of computers equals x times -3x plus 360. And then what I would do is go ahead and distribute the x. So there's going to be negative 3x squared plus 360 times x. And in the question, I said to find the maximum. Well, that's good news, because if you look at the graph of this, it's an upside down parabola because of the negative 3x squared. And so that means it does have a maximum. So now take the derivative. So that's a negative 6x plus 360. Whoa, my hand tried to write 360 too fast. So there's the derivative. And set the derivative equal to 0. And there's just 2 more steps to go. One would be add 6x to both sides. So now it's a positive 6x equals 360. And then divide both sides by 6. So 36 divided by 6, that's a 6, and then it's going to have an extra 0. So it turns out, because X was employees, it turns out they should have exactly 60 employees. That is the most, or excuse me, that is the number of employees they should have to have the most productive situation possible. So turns out that the boss went and hired a mathematician to figure out, you know what, you got 60 employees, that's exactly what the math says you should have. Well, Daisy, do you have any questions?
No, I think it's just practicing more problems like these and then it'll get easier.
Yes, that is definitely true. Yep.